In this session, I'll be going to explain proportional derivative controller, and here these are the presentation outline for this session. So in this session, I'll be explaining proportional derivative controller output, physical understanding of proportional derivative controller, significance of proportional derivative controller, block diagram of proportional derivative controller with second order standard differential system. Then we'll derive transfer function for PD controller, and then I'll explain limitations of PD controller, and at the end I'll sum up this session with advantages of PD controller. So basic control system that we have it in control closed loop system, that is having major two blocks, those are controller and plant. And if we see output of plant, that is what we are giving over here in feedback. So input to controller, that will be always a difference in between input and output, which is even called as error signal. And output of controller, that is what? Manipulated signal. So here in this session, this controller, that is what we are using as a proportional derivative controller. So let us begin this session with first point, which is what? Proportional derivative controller output. So here controller input, that is what? Error signal, as I have told you initially. So here input, that is what? Error signal. In time domain we referred that as AT. And controller output, that is even referred as manipulated signal, and that signal even we can refer as empty in time domain. So first I'll explain what is the transfer function of controller output in terms of S domain as well as in terms of time domain. So let us begin it. So when we talk about controller's output, so at that time controller output empty, that is algebraic addition of output due to proportional controller as well as derivative controller. So proportional controller's output, that is Kp into Et plus derivative controller's output, that is Kd into Det by dt. Now if we do Laplace transformation, so by Laplace transform we can have this time domain signal into S domain signal. So now it will be Ms is equals to Kpes plus Kpes into differential part of that will result into multiplication of Sth. And I can rewrite this in terms of Ms is equals to Es into Kp plus, this is Kd, Kp plus Kd into S. So this is what my controller's output, which is based on error input signal. Now let us try to understand what is the significance of proportional derivative controller and what is the physical understanding of it. So here error signal, which is what we are giving at input of proportional derivative controller. So this error signal, which is what we are giving at input to proportional derivative controller. So here this is what the input, which is what we are giving it to proportional controller as well as derivative controller. Now let us try to understand how output will come. So proportional controller, that is having output based on Kp only. So if I say Kp is equals to 1, then output of proportional controller, that will be similar to input, which is what? Error signal, that is what you can see by this line. So if Kp is equals to 1, error signal will be same, and if Kp is equals to more than 1, then this gain will be more, but shape of signal will not change. So shape of signal, that depends on other controller, shape of signal does not change by proportional controller. Now what happens with derivative controller? So for derivative controller we have output, that is kd into det by dt. Now what is det by dt? Here this is what time. So this signal that is changing with respect to time. Right now this is what error input signal. So det by dt, that is what slope of this line. So what happens is when I calculate slope at this instant, that slope will be this. So this is 0. Now if I calculate slope at this instant, this slope will be this. That is what? Negative slope. If I calculate slope at this instant, that slope is more negative. Over here one can see slope is negative. So see, at every instant we can see slope. Over here again it is 0. Now as if we slope over here, that is now it is changing to positive. So ultimately slope, that is what the case which is what we need to consider at output of derivative controller. So here as I can see slope is 0, so output of derivative controller is 0. Now slope is negative, so now output of derivative controller, that will be negative. Until here slope is negative, so output is increasing negatively. Now from here slope is positive, so now output will start to increase positively. So see, this is how we can understand output of derivative controller. So output of derivative controller, that is purely based on slope of error signal line. So if that slope is negative, in that case output will increase negatively. If slope is positive, in that case output will increase positively. So this is how output of derivative controller is there. Now what is the significance which is there with PD controller? So here I'll explain the basic significance which is there with derivative controller. So one can clearly see derivative controller accelerates output as acceleration of error is there. So signal is getting accelerated as error is getting accelerated. So derivative controller, that is having that significance, which is what explaining what should be the output, that is what getting accelerated based on acceleration of error. What is acceleration? Acceleration means rate of change of error with respect to time. So if error is changing faster, output of controller is getting change faster. If error is getting change slower, output of controller will change slower. So this is extreme significance, which is what people are using it in so many control system. So basic significance which is there with PD controller, that is it accelerates signal as error is accelerating. So if error is getting accelerated error means dE by dt is more. In that case, derivative controller even will get accelerated. So this is a significance which is what very useful to control so many system, and that is why PD controller is so important in control system. Now let us move with next point of this session, that is what block diagram. So here one can clearly see this is a basic block diagram of controller, where this is controller section. So this is controller section and this is plant, and these two are in series, so both will get multiply. And here controller section, that should be even kp plus kds. So this is what I can say, this controller section, that is what addition of proportional as well as derivative controller, that is kp plus kd into s, and this is what plant section. Now I'll explain transfer function of this So to have a transfer function of this is what unity gain feedback, which is what we can clearly see. So transfer function of this system, that is, this is, if I say this is what GS, that is what multiplication of Kp plus Kd into S into omega square n divided by S into S plus 2 zeta omega n. Then transfer function of this system will be Cs by Rs, and that is Gs divided by 1 plus Gs Hs. And here we can clearly say Gs is Kp plus Kds into omega square n divided by S square plus 2 zeta omega n into S. And Hs, that is 0. So if we place that into this transfer function, then we will be having transfer function Cs by Rs, that is Kp plus Kd into S into omega square n divided by S square plus 2 zeta omega n S. This divided by 1 plus Kp plus Kd into S into omega square n divided by S square plus 2 zeta omega n S. And if we take LCM, this term will get cancelled from numerator and denominator. So we'll be having Cs by Rs, and that is Kp plus S into Kd into omega square divided by S square plus S into 2 zeta omega n plus Kd into omega n square plus Kp omega n square. Now again I will be rewriting this. So now this equation is Cs by Rs, that is Kp plus Skd into omega n square divided by S square plus, if I say this is what, 2 omega n S into, this will be now zeta plus Kd omega n by 2 plus Kp omega n square. So this is what the basic derivation, which is what we are having. Now if I compare this with standard second order differential equation for this system, then that equation is Cs by Rs, that we know, which is omega square n divided by S square plus 2 zeta omega n S plus omega n square. So now if we compare this, then what is that which is changing? So here natural frequency, that is getting changed based on Kp. So this frequency, that is getting changed based on Kp, and value of zeta, now that is getting modified with respect to Kd. So Kd, that is what getting modified with respect to zeta, and Kp, that is what changing omega n. So here Kp, that affects to omega n, and Kd means differential gain coefficient, that is what affecting value of zeta. So that is how things are happening with proportional derivative controller. Now let us discuss what are the drawbacks which is there with PD controller. So when we talk about drawbacks of PD controller, then one drawback, that is offset. So there will be offset in PD controller. One is there will be increase in damping factor. So increase in zeta, that we can clearly see this is what zeta dash, and that is what actually zeta plus kd omega n by 2. So this is what the portion which is getting increased because of additional differential controller. So these two are drawbacks which is there with proportional derivative controller. One is offset and second is it is what increasing damping factor. And that is what new damping factor which we can compare even. Previously it was zeta only, now it will be zeta plus kd omega n by 2. What are the advantages which is there with derivative controller? So there are so many advantages, that's why we used to have PD controller. One basic advantage is it will decrease maximum peak overshoot. Second basic advantage is it will decrease rise time. Third basic advantage is it will decrease settling time period. And fourth basic advantage which is there with this PD controller, that is it increases bandwidth. So it will increase bandwidth. So there are lots of advantages, and based on these advantages there are some drawbacks even, and that those drawbacks are offset as well as increase in damping coefficient. Thank you so much for watching this video. In next session I'll be covering PID controller, which is so interesting. So continue watching with this video, and next will be PID controller. Thank you so much for watching this video.